Okay, welcome to the 9th lecture, the only lecture I will do this week. Just to remind you, we were just finishing chapter 2. I was showing you in the last video how in practice you can control or make an algorithm that controls the local error by controlling the time step size. And the way to do this in an adaptive way is to actually compute two approximations of the value u at time tk, and to then one yk and one yk tilde with different consistency orders. So you take one value with consistency order p and one with consistency order p tilde, and you ensure that the more accurate one is at least one order more accurate. You give a tolerance epsilon greater than 0, and then given the value at the last time step, yk minus 1, compute those two approximations, yk and yk tilde, both starting with the same value with time step size hk. Once computed, you compare the error, or you compare the two values against the difference of the two values against your tolerance epsilon, and if that is less than 1, then you actually reduce the time step. So if this value yk minus yk tilde greater epsilon is bigger than epsilon, then you reduce the time step to h opt and you compute again. And if when you finished, if the time step is accepted, either in the next step the time step is accepted or it was accepted in the first place, then you set the next time step to be h opt, or you go to the last time, t minus tk. And one way of producing two such approximations, so yk and yk tilde, is by extrapolation. And that was basically done by taking two approximations with the same ERK, with the same explicit Runge-Kutta method, one with time step size h, one with time step size 2h, and so you take two steps with size h or one step with size 2h, and compute a new approximation y2 tilde, which extrapolates from those two values via Richardson extrapolation, and is has therefore a local error of order h to the p plus 2. So it's essentially consistency order p plus 1, and therefore you can use it in the algorithm above. So now yk tilde can be used here, and you can compute your hk opt. So there's a few remarks I wanted to add, so we start here. So remark 2.4.7. So thus y2 tilde up here in this formula, so maybe I give the number again if we need it later as well. So this was 227, and this was 228, and this was 226. So this y2 tilde is an approximation of u2 or with consistency order p plus 1, which is greater than p, and can be used in algorithm 2.4.2 to control the error, the time step. And yk plus 1 tilde in this algorithm can be computed cheaply via formula 227 from y2 and or yk plus 1 in the kth step and capital YK. So essentially with index k plus 1 instead of 2. And as I already said in remark 2.4.4, in practice, of course, we expect better global accuracy if we use also for the next time step yk minus 1 tilde instead of yk minus 1 as the initial value for the calculation at the next time step. For computing yk plus 1 and capital YK. So for the theoretical result, we said we're computing y2 and y1 starting with y naught or with u naught. But in practice, you will of course take the y tilde values as your initial condition for the next time step. However, and this is now setting up the next subsection, in general, when we compute, even though we're using the same explicit Runge-Kutta method, the computation of y1 in theorem 2.4.6 requires, of course, different s-1 additional evaluations of the right hand side, because the stage values are not evaluated at the same places of f, since the stage values even if the time points where we're evaluating them might be nested. So if we're taking, for example, time steps at a half and full at the full point, then of course the method that takes two small time steps has the same stage values, or the stage values for that method include the points for the one which takes only one big time step. But the second argument in f, namely the y argument, will be different. So you need to evaluate it separately. So the stage values will differ from those of y1 and y2. So in total, leading to a total of 3s minus 1 function evaluations. For 2 time steps of both methods. For 2 time steps. For this p plus 1 order. So it is a p plus 1 order method, but it's not an optimal p plus 1 order method. It needs 3s minus 1 evaluations. And an alternative we will look at now, an alternative that uses the optimal number of stages. Remember the butcher barriers, that uses the optimal number of stage values S for a p plus 1 order. Method and reuses all stage values of the lower order method will be discussed now. So this comment basically says, okay, extrapolation as I did it in the theorem last time and explained revised today is one way of computing 2 approximations of different order and to run a time step control, but it requires 3s minus 1 function evaluations to get a p plus 1 order method, where the s is the s from the for 2 steps, yeah. So this means it's essentially 3 half s minus a half, which is more than the butcher barriers tell us for a p plus 1 order method. For lowish p's, p plus 1 order method requires only maybe p plus 2 stages or even p plus 1 stage. So embedded Runge-Kutta methods are the alternatively. Okay, let me just quickly answer this thing. Good. So an alternative is our embedded Runge-Kutta methods. So instead of estimating the local error by doubling the step size, these embedded Runge-Kutta methods use 2 methods of different order to achieve the same effect, as I just said. And as I said, the key to efficiency as the word embedded already says, is that the computed stage values GI are the same for both methods. So they only differ in the and only the quadrature weights for the final quadrature, namely the BI, differ. Okay, so definition. (2.4.8) embedded Runge-Kutta methods. So an embedded S stage. Runge-Kutta method with orders. So there's obviously two. We need two methods. So with orders of consistency P and P tilde computes two approximations, yk and yk tilde of uk with the same function evaluations. So as I said already before, but I in this definition make it precise for this purpose, the stage values gi and ki at the points t0 plus cih k are identical for all I equals 1 to s for both methods. That means both methods have the same coefficients aij and cj. aij and ci. And then to compute the final approximations, at time step tk, we use two different quadrature rules. So basically, yk equals yk minus 1 plus hk sum I equals 1 to s bi ki. Sorry, I just have to double check that that's correct, what I'm saying here. And yk tilde is equal to yk minus 1 tilde, or yk minus 1 because they both start at the same point, sorry, plus hk sum I equals 1 to s bi tilde ki. And that's 233. So here we have bi and here we have bi tilde. Such that I write it in here, such that the yk and yk tilde are consistent of order p and p tilde greater p. respectively. And typically we have simply p tilde is p plus 1. And as before, we can write this in a butcher tableau. So the butcher tableau for the embedded method has the form, as we know that both of them have the same aij's and ci's, we can just simply have only one tableau up here, because both of them have the same tableau anyway. All we do is we essentially add an extra row down here, so that we have two quadrature formulae down here. One with the b tildes and one with the b's. Okay? Now, I'm almost finished with this chapter. Just one more remark, and then I'm gonna give you the sort of most popular embedded Runge-Kutta method, which is also the basis of ODE 4.5 in MATLAB. But first, let me just finish with this remark. For higher order methods, or for functions, f of tu with complicated evaluation, most of the work is in fact the function evaluation. So this is exactly why we considered these embedded methods. Most of the work lies in the computation of the stages. And thus the additional quadrature rule is kind of for free almost. The additional quadrature for the evaluation of yk is almost free, almost for free. Nevertheless, due to the different orders of approximation, yk tilde is much more accurate, one order more in fact. And we can again estimate the error. We obtain that the uk minus the lower order approximation yk is equal to yk tilde minus yk plus O of h to the p. So this method is order h to the p, so the difference between this and this will be order h to the p, because this is p plus 1th order. So you see immediately that you can estimate the error by looking at essentially yk tilde minus yk, and we're back at our algorithm for time step adaptation. Thus yk tilde minus yk is a good estimate for the local error, and can be used again in algorithm. What's the algorithm number again? 2.4.2 for time step size control. However, and this is just to not forget this point, as in the case of extrapolation in the previous subsection, in practice, in practice we use again the more accurate method as the initial value for the next step. As in the case of extrapolation, in practice we use the more accurate value yk minus 1 tilde as the final approximation at tk minus 1, and thus also as the initial value for the next time step. Even if in this case we don't have the computable error estimate, but it won't be worse than the error we make. Global error won't be worse than with the lower order method for sufficiently small h. And as I promised, we will finish, or I'll finish the chapter with the most popular adaptive explicit Runge-Kutta method, namely the dormant price for 5 embedded Runge-Kutta method, which constructs two approximations for UK, one yk tilde of order 5 and one of consistency yk of consistency order 4, and has the following butcher tableau. So I guess this this had to be established by somebody in order to satisfy all the order conditions up to order 4 and 5, and leads to these rather complicated fractions, but it essentially has, so the first of the two here has order 5, the second has order 4, and both have the same stage values. Okay, and this is the backbone of the MATLAB ODE solver, ODE 4.5. So this is the typical explicit Runge-Kutta method solver in MATLAB. Okay. Good. So that is the end of chapter 2, explicit methods. So we've now got a toolkit for solving ODEs. If we make the time step size smaller, we get better approximation, but we have a few points we need to worry about and set up for the next chapter. And in particular, remember that all our results were having this e to the lt factor in them. So we somehow need to overcome this problem. So just a few points of reminder. So in chapter 1, we studied methods for the solution of initial value problems and the analysis, in chapter 2, it should say, not in chapter 1. So in chapter 2, we studied methods for initial value problems and the analysis of their convergence with shrinking step size h. And we were able to gain a priori error estimates from consistency and stability. For sufficiently small h. But all of those estimates, and now I'm repeating what I've already said, all estimates were based on Grunwald's inequality and all contained a factor, a term of the form e to the lt, where L was the Lipschitz constant of f. So obviously, if we're now thinking about long-term, so this chapter is about long-term integration, long-term stability. If we're thinking about long-term, then this factor e to the lt obviously increases very fast, exponentially fast, with increasing length of the time interval, 0t, on which we're integrating, and is thus unsuitable for the study of long-term integration. Eventually, the exponential term e to the lt will always outweigh any term of the form h to the p for any h and for any p. So we can take as high an order method we want and as short the time step as we want. The exponential term will always grow faster. On the other hand, we do really need to, or we do really want to study long-term processes. So for instance, our solar system has been moving on stable orbits, satisfying ODEs, initial value problems, namely the Newton's law of motions, Newton's laws of motion for several billions of years. So clearly, and there is no, and we do not observe exponential growth of the velocities, or an exponential increase of velocities. So there are applications for which the simulation of long time periods is worthwhile. And where this exponential growth of the solutions of the errors would be very disturbing. Okay, so that's what we will look at now. This chapter now studies conditions. So these are now conditions on the differential equations that we want to exploit. So it's not true for every differential equation. So in general, the results that we showed in the previous chapter are true. If the Lipschitz constant, if we have only got this general Lipschitz constant, and we are integrating over a long time interval, then any method, or for some initial value problems, any method will lead to an exponential growth in the error. But certain initial value problems do not have that property, and we will now discuss those and then come up with numerical methods that mimic that behavior. So we're going to look at monotonic initial value problems. And a certain type of, or two types of those monotonic initial value problems are those for which we expect kind of no exponential growth or stability of our solutions. So in order to do that, we consider sort of the simplest initial value problems we can kind of think of for some complex constant lambda. We look at the scalar linear initial value problem u primed is equal to lambda u, and u of naught is equal to 1. So this would be 3.1. And we are looking at complex constants here, because the two parts of this complex constant have two different roles in our problem. So splitting the lambda into real part plus imaginary part, the complex valued solution to this problem is, you can just do an ansatz and find it. Well, we know that as in the real case, this problem is essentially given by the exponential function of lambda t, but because lambda is now complex valued, this exponential can be also written as real part of lambda to the t. So this is a generally exponentially growing or decreasing function times an oscillatory function, cos imaginary part of lambda t plus I sine of imaginary part of lambda t. And now we can kind of study the behavior of this very, very simple model ODE. So we see that there is a exponentially growing or decreasing part and an oscillatory part that doesn't grow or decrease in size. So if we study the long-term behavior, so the behavior of u of t as t goes to infinity is determined, what it does at infinity is determined by the real part of lambda, because the other part only oscillates all the way up to infinity. But the exponential function obviously has three regimes. Okay, we have the regime real part less than 0. Then the solution, in fact, the entire solution has to go to 0. No matter what the oscillatory part does, the prefactor here goes to 0, so the whole function has to go to 0. If the real part of lambda is equal 0, then this thing here would just be 1, and we're only left with this oscillatory function, which doesn't change in modulus, and so basically we know that the modulus over all time is 1. And finally, if the real part of lambda is bigger than 0, then the solution has to blow up. So it's really exponentially growing. So in that case, there's no surprise that our error will also exponentially grow, because the function itself, of course, grows exponentially. Let me just highlight this. So we've got the three regimes. And of course, both the first and the second case, in both of those cases, the solution is bounded. In fact, one case it's actually bounded by 0, or is going to 0. Moreover, the solution is bounded for lambda with non-positive real part for all points in time. Okay, and another remark about the presentation in this lecture notes or in this lecture. So this is a general remark for the whole chapter. So we will again and again deal with eigenvalues of real valued matrices. And even if the matrix is real, these eigenvalues can be complex, can be complex valued. And so we will always, from now on, consider complex valued IVPs. So just bear that in mind. In the previous chapter I was mostly keeping it real, but here, because essentially the lambda in this model problem here plays the role of one of the eigenvalues. So if I have a linear ODE system, then that would just be u primed equals a times u plus b, and it is in fact the eigenvalues of this linear matrix, of this linear operator of the matrix A, that control in which of these three regimes here our system of ODEs, more complicated system of ODEs, would fall. Or even in a nonlinear setting, the eigenvalues of the Jacobian matrix at a point will control in which regime it falls. And so since these can be complex valued, we just simply work with complex IVPs from now on in this chapter. So due to Gronwall, I'm just repeating what I already said at the introduction of this whole chapter. And due to the stability theorem, (1.4.5), the solution to the IVP in example 3.1.1 above always admits a bound at all times, admits the estimate u of t less than or equal to e to the modulus of lambda t u of naught. So we can always bound it at all times, and this can be seen easily by using theorem 1.4.5 with comparison function v of t equals 0 everywhere. But as soon as lambda is in fact non-zero and has a non-positive real part, so 0 or negative, then although being correct, the estimate is very pessimistic. So we know the solution decreases or goes to 0, but the upper bound that we found here is kind of growing and growing and growing with e to the modulus of lambda times t, and therefore useless for larger t. So as I said already, since problems with bounded long-term behavior are quite important in applications, I've already given you some examples, let's write it out. So since problems with bounded long-term behavior are very important in applications, we have to introduce some improved notion of stability for those problems. So we can't treat all problems in the same way. So problems where the real part is positive or has one positive eigenvalue or many positive eigenvalues will have exponentially growing solutions, but for those which do not have that, we need a new notion of stability. And this new notion of stability is very similar to the old one, but significantly different. So in particular, instead of the Lipschitz condition we had before, we now define on again some domain D subset R cross C to the D, we define a one-sided Lipschitz condition. And this one-sided Lipschitz condition is here. It's got number 3.3. Let me just see if I didn't forget any numbers before. 3.2 and 3.1. Yeah, we've got them both. So the one-sided Lipschitz condition is given here. So the real part of f of ty minus f of tx in a product with y minus x has to be less than or equal to some constant nu times y minus x squared. I will discuss in a minute how it relates to the standard notion of Lipschitz to the standard Lipschitz condition. But for the moment, just let's call it a one-sided Lipschitz condition. For some constant nu, and importantly, this nu can be positive or negative. This has to hold for any points tx and ty in this domain of definition for our function f. And then secondly, such a function is called monotonic if this nu can be chosen to be equal to 0. So if the real part of the product of f ty minus f tx with y minus x is in fact non-positive, less than or equal to 0. That's 3.4. And then ODE is that has such a monotonic right-hand side function, f is called itself monotonic. So the ODE is also called monotonic. So I promised that I would link it to the classical notion of the Lipschitz condition we had in the previous section. So the term monotonic is consistent in this definition is consistent with the term monotonically decreasing which we know from scalar real-valued functions. And we can see this quite easily. So I'm just going to look at a scalar real-valued function by observing for some f from R to R, and a value, real value, y bigger than x, the product of f t y minus f t x times y minus x, which is in fact for real valued functions the same as the real part of the scalar product of f t comma y minus f t comma x with y minus x. And since we assumed that f is monotonic in the sense of the definition, then this is less than or equal to 0, which actually in fact is equivalent to f of ty minus f of tx is less than or equal to 0. F of ty minus f of tx being less than or equal to 0, because we can just cancel this y minus x because we assumed y is strictly bigger than x. So it doesn't change the inequality, and we can divide by it because it's non-zero. So here is now a sharper stability result. It uses again Gronwall's inequality, but now instead of assuming standard Lipschitz condition, we assume this one-sided Lipschitz condition, and under this one-sided Lipschitz condition for f, we have this new stability result. So this is now again stability under one-sided Lipschitz condition. Okay, let u of t and v of t be the solutions of the two ODEs u primed equals ftu and v primed equals ftv, so the same ODE, but with two different initial values. U of t naught is u naught and v of t naught is v naught. Both posed as ODE initial value problems in c to the d. Then let the function f R cross CD be continuous, and let the one-sided Lipschitz condition, there should be a D here, sorry, D subset R cross CD. So F is defined on D, which is a subspace of R cross CD. On that D, we are assuming the one-sided Lipschitz condition that we had in the definition 3.1.4. Then under that one-sided Lipschitz condition 3.3, we have for t bigger than t naught that the v at time t minus u at time t in modulus is less than or equal to e to the nu times t minus t naught v of t naught minus u of t naught. So you see that the nice thing now is that in our monotonic case, So if we're in the monotonic case, then nu is 0, so this would be simply 1. So in the monotonic case, the error in the solution v of t minus u of t is always less than or equal to v of t naught u of t naught. And in the case of nu being less than 0, so negative nu, we even know that it has to be dampening exponentially. So the dependence actually goes to 0. This is 3.5. Okay, let me prove this. So in order to prove this based on the one-sided Lipschitz condition, we consider an auxiliary function. We consider the auxiliary function m of t being the norm, or the modulus rather, of v of t minus u of t squared. And also consider its derivative. So let's write this out. What do we get? M primed of t is 2 times the real part of v primed of t minus u primed of t with v of t u of t minus u of t. Now we can use the ODE. So we know that this is f of t and v, and this is f of t and u. So we in total get that that's less than or equal to, using the one-sided Lipschitz condition, we know the real part of f of t and y minus f of t and x with y minus x is less than or equal to y minus x modulus squared, nu times y minus x modulus squared. So here we can just apply this with the argument being v and u. So this is, well, first of all, this is equal to 2 times real part f of t and v of t minus f of t and u of t inner product with v of t minus u of t. And now we use, this is exactly the formula from the one-sided Lipschitz condition. So we know that this is less than or equal to 2 times nu times f of, or not f, f is gone, v of t minus u of t squared. And substituting back, modulus v of t minus u of t squared is nothing else than m of t. So we end up getting that this is equal to 2 times nu times m of t. So if we now look at what the first derivative satisfies, so we have m of t is that, and then prime of t is 2 nu mt. And so if we now look back, and I recommend you stop the video and have a look back, or take your lecture notes to look at Grunwald's inequality again. So according to Grunwald's inequality, which was lemma 3 1.1.8, sorry, 1.3.8, which is on page 10. We obtain for t greater than t naught that we have m of t being actually less than equal to m of t naught times e to the 2 nu t minus t naught. And then finally taking the squares, taking the square root yields the stability estimate. .5. Finished. Okay, so we now know that v of t minus u of t in modulus is less than or equal to e to the nu t minus t naught times v at times t naught minus u at time t naught. We can go back to our example. So remark (3.1.7). So as in example 3.1.1, we obtain from this new stability estimate that for the difference of two solutions u of t and v of t, of the differential equation u primed of t equals f of t u of t, both with, as before, with different initial conditions, in the limit as t goes to infinity, we obtain for nu less than 0. So again, looking at the regimes from the example 3.1.1, as nu is, when nu is less than 0, I already said this, v of t minus u of t goes to 0 as t goes to infinity, and when u equals 0, then we get that v of t minus u of t is actually less than or equal to v of t naught minus u of t naught. So you have essentially no growth of the error, at least. The difference in these two solutions of the initial value problem. So this is only still talking about continuous problems. So far we've just looked at stability again. So let me just recall what I've just said. So I told you that in the previous chapter we had a based all our results on Lipschitz, a global Lipschitz condition, and we ended up with this extra factor e to the lt in all our bounds. So as t grows, as the capital T goes to infinity, eventually this term will swamp all our h to the p terms in our approximations, even if p is very large and h is very small. So we have to restrict ourselves to a subclass of initial value problems, and to do so we look at the model 1D complex initial value problems given in 3.1 here, which has 3 regimes depending on the real part of lambda. And then we said that for 2 of those regimes, namely if the real part of lambda is non-positive, we can get sharper stability result for the continuous setting, no discretization yet, namely the one-sided Lipschitz condition given here in 3.3 is a sufficient criterion to guarantee stability. So given 2 solutions with 2 different initial conditions in the d-dimensional complex plane, and f satisfying this one-sided Lipschitz condition, then we have this stronger stability result here. It also improves the result from before, even if lambda is positive, or if you have a system and some lambdas are positive, because the nu is actually could be slightly smaller than the capital L, the global Lipschitz condition. Okay. So let's now apply this to a linear system of ODEs, as I said. So this is like essentially application to a linear system of ODEs. Let A of t in C d cross t, so even the matrix system I'm making complex valued now, but we assume that it's at least diagonalizable. So let this A be diagonalizable, and with eigenvalues given by lambda j of t for j equals 1 to d. And we consider the ODE with the linear right-hand side, f of ty equals at times y. If then for this linear setting, we always have a one-sided Lipschitz condition. So it does satisfy a one-sided Lipschitz condition on all of R cross CD with this one-sided Lipschitz constant nu being the maximum of the real part, so the maximum positive, not the modulus, really the maximum real part of the eigenvalues of this matrix valued function at time t. And the linear differential equation with that f as right hand side is in fact monotonic if and only if all real parts of these eigenvalues are non-positive for all times. So if the real parts of these eigenvalues are non-positive for all times t, then if and only if that's the case, then the linear ODE is monotonic. And this is essentially the vector valued form of example 3.1.1. So let's just prove this. So the statement is, if we have a diagonalizable matrix valued function with eigenvalues lambda j, then the one-sided Lipschitz condition holds with nu being the maximum of the real parts of these eigenvalues lambda j at all times t. So for the right hand side of the ODE, we consider now this condition. We have real part of f of y and y minus f of t and x. So in the linear setting, that's at times y minus a of t times x with y minus x in a product. I exploit the linearity, so I get real part of a of t y minus x with y minus x divided by y minus x squared and times y minus x squared. And I added and divided and multiplied with this square, because then this is just the Rayleigh quotient, and so this is essentially bounded from above by the maximum eigenvalue of a of t. So this is in fact bounded above by maximum j equals 1 to d real part of lambda j of t times y minus x in modulus squared. And so this thing here would be precisely our nu. So this shows that nu less than equal to is less than equal to max j equals 1 to d over all times t in R of the real part of lambda j of t. So we have at least that nu is less than or equal to this. If we now insert for this y minus x in this inequality an eigenvector of a of t corresponding to lambda j of t, for which this maximum is attained, then of course we have equality. So then we obtain the equality, not the equality. And so nu is in fact not just less than or equal to, but it's equal to max j equals 1 to t dt in R real part of lambda j. Okay, so we now know that linear ODEs always satisfy this one-sided Lipschitz condition, with nu being the maximum real part of the eigenvalues of the linear operator, or of the matrix defining the linear operator. So for the final part of this lecture today, let me start now to consider what this class of, or a class of initial value problems that satisfies these conditions, and that is for which it is interesting, which is interesting in applications, and for which we can obtain more bounded or better bounded long-term error bounds. And for this purpose, we introduced the term stiff. So stiff initial value problems comes from elasticity, where it's controlled by the stiffness of material controls this behavior. So example 3.1.9. Now we need to go to, we can't just study a single scalar valued initial value problem. We need to look at least at two, and here we're going to look at a three-dimensional problem. So again, we take an autonomous linear ODE, so U primed is A of U, and with a very particular matrix constant matrix function A minus 21, 19, minus 20, 19, minus 21, 20, 40, minus 40, minus 40, and use as initial condition U of naught is 1, 0, minus 1, and we call this equation 3.8. So as I said before, what controls, or in the previous lemma, what controls the stability and these one-sided Lipschitz condition are the eigenvalues of this matrix A. So let's study the eigenvalues of A. They are lambda 1 equals minus 2, and lambda 2 and 3 equals minus 40 plus or minus 40 I. So they're complex valued, lambda 2 and lambda 3. So this you can do yourself. To compute these eigenvalues, just write down the characteristic polynomial for this matrix and solve the quadratic equation or the cubic equation that comes out in this case. Or you can just check that it satisfies the determining condition, because I've given you the eigenvalues. And therefore the solution, again using the formula I gave you already for example 1, is a half e to the minus 2t, this comes from the lambda 1, plus a half e to the minus 40t, that's the second and the third eigenvalue, the real part, and then we have cosine 40t plus I times sine 40t, and the second component is similar, minus a half e to the minus 2t plus a half, minus a half, sorry, minus 1 half e to the minus 40t cosine of 40t plus I times sine of 40t. And finally, the last component is simply minus e to the minus 40t cosine of 40t minus I sine of 40t. And this clearly goes to 0 as t goes to infinity, or let's write it here, as t goes to infinity. So all of the real parts are negative. So here this goes to 0, this part goes to 0, so the oscillatory part doesn't really matter. This part, this part, this part, all these parts converge to 0, so the whole u of t converges to 0 as t goes to infinity. And so now this is now a generic problem where we have this case where the solution goes to 0 as t goes to infinity, but the problem is that the two parts here actually go to 0 with a different rate. This is not really a good idea. Oh yeah, this works. So let me just rewrite this to t. So here we have, on the one side, we have a thing that goes to 0 with e to the minus 2t, and here we have e to the minus 40t. So the second part decreases much more rapidly than the first part. So these oscillatory parts will die out much more quickly than the non-oscillatory parts. And so for small time t, because you have the oscillations, you expect that you have to actually do small time steps to capture all that. So for small t, for small time, 0 less than or equal to t less than or equal to 0.2, because 40 times 0.2 is 8, so e to the minus 8 is 3 times 10 to the minus 4. So this bit here at 0.2, this bit here will be in the order of 10 to the minus 4. And so, whereas this bit here will be of the order e to the minus 0.4, which is 0.67. So this bit, on the other hand, will only be 0.67. So this thing will be almost disappeared, whereas this bit is still fairly large. So all three components are changing rapidly for small t up to 0.2 roughly. So this is a rough estimate where the number is small enough due to the trigonometric terms. In all three parts, since the factor e to the minus 40t in front of them is still fairly large, and thus it is necessary to choose a small time step size. H much smaller than 1. If when we basically for bigger times, bigger than 0.2, I've already said we have u2 will be almost 0. It will be of the order of 10 to the minus 4, because essentially here you have this is of the order of 10 to the minus 4 and this is of the order of 1. So u2 will be of the order of 10 to the minus 4, and equally because these two terms will also be negligible, u1 and u2 will be essentially almost the same. And u1 will be, so u3 will be approximately 0. And u1 will be approximately equal to u2. And both those u1 and 2 components change fairly slowly. In fact, they're just going to 0 very smoothly, e to the minus 2t. So we could choose a large time step size. Bigger than or equal to 0.1. So basically, if you just look phenomenologically, you see that for short near 0 time near 0, this oscillatory part is still important, and especially when t is almost equal to 0, this will be very important. It will oscillate very fast. But after a certain time, namely after about only 0.1 or 0.2 time units, these parts will be gone, and essentially you just have this part of the solution. And so you can suddenly start integrating with quite large time steps. However, and I will finish this because we only do one lecture this week anyway, so let me just finish this this motivation. I'll pick it up in the next video. If we consider the explicit Euler method applied to this system, 3.8, we get yn, well, let's stick to the notation that we, yn, which is equal to yn minus 1 plus h times a yn minus 1, or in other words, if we substitute y identity plus ha times yn minus 1, and that's equal to identity plus ha to the n u naught. Now if we choose a step size of h equals 0.01, so fairly short, the matrix I plus HA has eigenvalues mu1 equals 1 plus 0.01 times minus 2. That's the first eigenvalue, or lambda 1. Which is 0.98. And mu2 would be 1 plus 0.01 lambda 2, which is 0.6 plus 0.4i, and then mu3 is simply 0.6 minus 0.4i, and therefore if I look at our formula, we see that the norm of yn, or the modulus of yn, is equal to modulus of I plus ha to the n u naught is less than or equal to norm I plus ha to the n norm u naught, and I can bound this by the largest of the eigenvalues, and you can actually figure out what this norm is, and it's essentially 0.98 to the n, and the norm of this is square root of 2. So here was the initial condition. So the initial condition was 1, 0, minus 1. So that has norm square root of 2. And the spectral norm of the, so this is the 2 norm. The spectral norm of the matrix I plus HA is of course the largest eigenvalue here in modulus, and 0.98 here. Oops, is the largest of the eigenvalues. And clearly, because the largest eigenvalue is less than 1, this goes to 0 as t goes to infinity, or as n goes to infinity. So which is at least qualitatively the correct behavior. However, if I now took h to be 0.1, then I plus HA has now got eigenvalues. Mu1 is 1 plus 0.1 lambda 1, which is 0.8. But now the other two, mu2 and mu3, would now become minus 3 plus minus 4i. And now it's not this guy, but it's these guys that are the largest in modulus. And we would then get, you can read up in the notes, I will come back to it like next time, you will then get that the for the eigen, if we take the eigenvector v2 or v3 eigenvector corresponding to mu2, mu3 respectively, then I plus HA to the n applied to any of those two will be not just less than or equal to v, but equal to minus 3 plus minus 4i to the n norm vj, but this is an eigenvector, so this is equal to 1, and the nth power of I plus HA applied to Vj is 5 to the n, which obviously goes to infinity as n goes to infinity. So if we if u0 contains components in the direction of, so this is for j equals 2 and 3, if u0 contains components in the direction of v2 or v3, we get that yn will be going to infinity as n goes to infinity, and very much in contrast to the behavior of the exact solution. Which goes to 0 as t goes to infinity. So even when u2 is approximately u3 and u1 is approximately 0, say at time t equals 0.2, and thus the perturbations, and if the perturbations are very small, so let's say you take one time step, you've made a small perturbation, and then you try to iterate with a time step size of 0.1, the instability of explicit Euler with time step size h equals 0.1 will lead to an exponential increase in these perturbations. So as I said, if we look at the time axis, so let's assume we start with t equals 0 here, and here is t equals 0.2. So we have some oscillatory behavior. So the first component maybe does something like this, and it dies out these oscillations, and the other component would maybe do something like this. Yeah. Even if we took a very small time step, so even if we do here time step h equals 0.001 or something like that, we will have a little bit of an error here. So we will have here at this point, we will have u1 or y1 rather. Y1 will be only approximately equal to u1, which will be approximately equal to 0. Y2 will be approximately equal to u2, which will be approximately equal to u3, and thus to y3. So if I now said, okay, from now on the ODE actually doesn't do any bad things anymore, and I choose 0.1 here, then I will end up, let me leave a bit of space here. So if I choose now the time step size to be h to be 0.1, then maybe, although these things are, or the one thing is already almost 0, it will basically start to oscillate, and then eventually it will blow up, because we know that there is a small proportion of the error will be in the direction of the second and the third eigenvector, and I plus HA to the n Vj with H mesh size, step size chosen 0.1 increases with exponentially with 5 to the n. So even if the error at that point here is 10 to the minus 4, after a certain number of time steps, you've multiplied that error by 5 to the n. Okay, I'll stop here and formulate this more precisely next week. So this is it for this week. No second video, and I'll see you next week. Bye.